Hi, in this video we are going to talk about another very important shortest path algorithm, the so-called Bellman-Ford algorithm. So let's get started. This algorithm was invented in 1958 by Bellman and Ford independently. Basically it is slower than Dijkstra's shortest path algorithm. But it's very important that on the other hand, it's much more robust because it can handle negative edge weights as well. We have been talking about Dijkstra's algorithm and I have mentioned that it can only handle positive edge weights with weights greater than 0. In this case, we can use positive as well as negative edge weights as well. Bellman-Ford algorithm is going to cope with all of them. Dijkstra's algorithm chooses the edge greedily with the lowest cost possible. On the other hand, Bellman-Ford algorithm relaxes all edges at the same time for v-1 iterations, where the v denotes the number of vertices. And basically this is the most crucial difference between Dijkstra's algorithm and Bellman-Ford algorithm. For Dijkstra's algorithm, it relaxes a single edge at the same time. Here for Bellman-Ford algorithm, it relaxes all edges at the same time, but several times for v-1 iterations. The running time is ordo v times e, where the v denotes the number of vertices, the e denotes the number of edges in the graph, so it is slower than Dijkstra's algorithm, but on the other hand, it is much more robust. Bellman-Ford algorithm does v-1 iterations plus one more to detect cycles. If the cost decreases in the vth iteration, then there is a negative cycle. We can know it for sure because all the paths are traversed up to the v-1 iteration. So we are sure that if we make another iteration and the total cost decreases, it's sure that there's a negative cycle. So just to be clear, what is a negative cycle? What's the problem itself? If we would like to find the path with the minimum cost, we have to go from A to B, B to C, and back from C to A in order to decrease the overall cost. Why? Because in order to go from A to B, it takes 1 unit. In order to go from B to C, it takes minus 10 unit. In order to go from C to A, it takes 5 unit. So the overall cost will be smaller than 0, which means that if we make several of these cycles, we are going to decrease the overall cost. And if we are looking for the shortest path, the minimum path, of course, the algorithm is going to tell us that we have to make infinite loop in this negative cycle. So basically that's the problem. Real life scenarios, of course there are no negative cycles. For example, for Google Maps, of course there are no negative cycles because it would mean that you have to take several cycles and it's going to decrease the cost. Of course it's not going to happen. So in real life scenarios, no negative cycles at all, but sometimes we transform a problem into a graph with positive and negative edge weights and looking for some negative cycles. For example, if we are dealing with stock market or forex related data, we are able to find the so-called arbitrage situations and make riskless money, and we are looking for these negative cycles. So in that situation it's crucial to find these negative cycles. So what about the Bellman-Ford pseudocode? We have the function Bellman-Ford algorithm. It's going to have the vertices, so all the vertices in the graph, all the edges in the graph, and basically we have to define that what will be the starting vertex. We are going to set the minimum distance of the starting vertex to be equal to 0, so basically it is the initialization phase, and we set all the other vertices min distance to be equal to infinity and the predecessor to be equal to undefined. Then basically this is the core of the Bellman-Ford algorithm. We are going to relax all the edges at the same time. We have been discussing it and we are going to do it v-1 times. So for all edges, if the distance to the destination can be shortened by taking the edge, then the distance is updated to the new lower value. and we do it v minus 1 times. This is what's called the relaxation phases. And it is the same as you may recall Dijkstra's algorithm, that we have the temporary distance, which is the distance to u, plus the edge weight between u and v. And if this temp distance is smaller than the original distance, then we have to update the distance and we have to update the predecessor, as we have seen for Dijkstra's algorithm. And it's very important that this is the last step for Bellman-Ford algorithm. We have to make another check whether there is a negative cycle or not. Since the longest possible path without a cycle can have v minus 1 edges, and we make v minus 1 iterations here, so the edges must be scanned v minus 1 times to ensure the shortest path has been found for all nodes. And the final scan of all the edges is performed, and if any distance is updated, it means that there is a negative cycle. So that's why we have to make this final iteration and final check whether is there any better solution. Okay, and if there is, we know that, okay, there must be a negative cycle. And I said earlier, it's very important that you may pose the question that, okay, why is it good? We are not going to deal with negative edges, but several applications relies heavily on the fact that we can transform several other problems. For example, knapsack problem, or this forex related problem into a directed graph that has negative edge weights as well. And Dijkstra's algorithm cannot be used for negative edge weights, so we have to use Bellman-Ford. That's why this algorithm is very important, unlike the fact that, okay, the running time is not as good as for Dijkstra, but whatever, it is very useful sometimes. We have the so-called yen optimization. It was invented in 1970, that sometimes Bellman-Ford algorithm is very slow, so it would take a lot of time to finish its calculation. So we can have some optimization basically. We can terminate the algorithm if there is no change in the distances between two iterations. We have been talking about that we make v minus 1 iterations, where the v denotes the number of vertices in the graph. But maybe we just have to make a few iterations at the beginning, and further iterations are not going to change the final distances significantly, so we don't have to make the last few iterations. Why is it good? Because our algorithm is going to be boosted up and it's going to be faster. Basically, we use the same technique in bubble sort in order to boost it up. So what about the applications? We are going to talk a bit more about the applications of shortest paths in a distinct lecture, but as far as Bellman-Ford algorithm is concerned, cycle detection can prove to be very important. So negative cycles as well. We have to run the Bellman-Ford algorithm that can handle negative edge weights by default, and for example on the forex market it can detect arbitrage situations. What does it mean, arbitrage situations? It means riskless money. We are able to detect the so-called mispricing, and this mispricing can lead to, for example, convert American dollar to Canadian dollar to yen, and yen back to American dollar, and you are able to make some money because of the mispricing, because there are some arbitrage situations, and these kinds of situations can be found with the help of Bellman-Ford algorithm. I think a very useful and a very elegant application for Bellman-Ford algorithm. Thanks for watching.